Today we're going to talk about mirrors and lenses. And because many of you just skip to the end and look at the formula, I'm going to save you the trouble. Here are the formulas. 1 over f equals 1 over di plus 1 over do. That's the first one. And the second one is m equals h I over ho equals negative di over do. Alright, f is the focal length, which is 1/2 the radius of a circular mirror. Di is the distance to the image. Do is the distance to the object. Those are the same down here. Hi is the height of the image. Ho is the height of the object. And m is the magnification. Okay, there are your formulas. So those of you who just like to look at the formula and try to figure everything out, save you the trouble. Here it is. Feel free. Okay, for everyone else, I'm going to actually explain this topic and talk about all of the different situations. So there's your formula. Write it down. I will start talking today about plane mirrors just very briefly. I think this is probably going to all be pretty intuitive to you. But a plane mirror is just a normal mirror, a flat mirror, like many of us use every day. Okay, so here's our mirror. Okay, and if my eyeball is here looking at the mirror, okay, and there's a light source down here. Maybe there's a candle down here. Okay. The candle's light travels to a straight line of the mirror, where it reflects off the mirror to our eye. Okay. To us, when we see the reflection of the candle, we see the reflection of the candle over here. And there's some really good diagrams of this in the textbook, but you get the idea. This and this length are the same. Okay, that's an important idea. It looks to us like the candle is the same distance away from the mirror on the other side, the imaginary mirror world over here, as the candle actually is away, as the same distance as it actually is away from the mirror on our side. So that's just how mirrors work. I think everyone realizes this. So if we drew this, these would both be a couple of right triangles, except that was terrible. Yeah, these are both right triangles, so we can figure out stuff with lengths and whatever. We're not going to talk about plane mirrors much, but just it is important to realize that the length from the mirror to the actual object is exactly how far it looks like the image of the object is on the other side. This imaginary candle we can see is called an image, and we'll talk more about images as we go forward. And this is actually a virtual image because it's inside the imaginary mirror world. Okay, for certain convex and concave mirrors, the image isn't on the other side of the looking glass, as it were. Okay, let's talk about concave mirrors a little bit. If you remember from geometry, way back when, concave means it is vaguely shaped like a cave. So this is what a concave mirror looks like, approximately. Okay. We'll focus on circular concave mirrors, and they'll have a center out here, and if we continued them around, it would make a circle. It's not a great drawing, but I think you get the idea. Alright, from earlier, when I gave you the formulas, there was something called the focal length. The focal length is the midway point between the surface of the mirror such that the radius is perpendicular, and the center. So this is called the focal point. It's also called the focal length from F to, I'll call this M over here. From F to M is the focal length. Now we can let this be fairly complicated if we like. I don't have time this school year to let it get too crazy. Okay, but we've got, I don't know what that's supposed to be. We've got this object here. We could do something called a ray diagram, whereby we draw a parallel line here, and then we draw a line from that intersection point through the focal length, except that I can't draw. And then we draw this. Still can't draw. And I get there, and then back over here. And that point where those two lines intersect will show you where the image will be. And this is a weird thing. Concave mirrors, the image isn't on the other side of the mirror, it's somewhere over here. And if you had like a sheet or a projection screen or something, it would actually reflect the image and it would be here. And notice that it's upside down. It usually is for a concave mirror. Now you're not going to have to do all of this ray diagram stuff, but if you look in the textbook on about page 372, it breaks it down. It's really not hard. You saw that didn't take me long to do, even though I just kind of BS'd it. But we don't really have time to do ray diagrams because they are a little time consuming. We need to break out the straight edge and all of that good stuff. So don't worry about this. The big thing we'll do is use the mirror equation that I gave you earlier. So let's talk a little bit more about it. Okay, the mirror equation was the one that said 1 over F equals 1 over di plus 1 over do. And that's just, you're relating the focal length to the distance to the image and the distance to the object. You'll be given two of these and you'll be asked for the other one. Or they might give you the radius, but you just divide that by 2 to get the focal length. Okay, this is one of those equations, if you think about the algebra here, it's going to be kind of unpleasant. So we probably are going to want to plug in first and then solve for our variable, because otherwise this is going to get really, really gross. I mean, trying to solve this for f, we can't just flip it upside down. That's not how it works. So we have to multiply both sides by f, and then we have to divide by the sum of these fractions, and it's just gross. So yeah, my advice is to plug the numbers in first. Plug numbers, then solve. Just on these. Okay, and this is really going to be easy, because they're just, like I said, they're just going to give you this information. And that's not going to be bad. The other equation, I'll talk a bit more about it now. The other equation was the one for magnification. M equals H I over HO equals negative DI over DO. Okay, and the magnification just tells you, exactly what you think. How much bigger or smaller the image is from normal. A magnification between 0 and 1 is going to be smaller. A magnification greater than 1 is going to be larger. A magnification between -1 and 0 will be inverted, smaller. And a magnification less than -1 will be inverted, larger. Okay, so that's easy. When you get a negative height of the image, that just means it's inverted. This is a three-way equation. This is going to be simple too. They're just going to give you at least two of these, and you'll have to figure out the other stuff. It's a simple equation. Just think about what magnification means. It means how much bigger or smaller an image is. So that'll be simple. The tricky thing, and it's not that tricky, it's just you have to remember this, it will be that if, and in certain cases, here's your concave mirror, here's your object. Sometimes the image will be over here somewhere. Okay, so here would be your DO, your distance to the object, and here would be your DI, your distance to the image. If the image is in imaginary mirror land over here, then that distance is negative. This is going to be a negative distance. Okay. Whenever the image is not in the real world, whenever it's on the other side of the mirror, that's a negative distance. Anything that's over here is a negative distance. That's just something you've got to remember. And that really comes into play when we talk about convex mirrors. So this time our mirror is shaped like this. And the biggest weird difference here is going to be that the focal length is over here, right? Because the center is over here somewhere. So our focal point is going to be over here. So our focal length, F, is actually going to be negative here. Okay, and then we have an object over here. This will be positive. D to the DO will be positive. And then you have to use the equation to figure out where the image will be, and it'll depend on angles and lots of different stuff. But our mirror equation still works, so we still use our same old thing. But just remember that a negative length on these problems means that it's a length this away. These are negative lengths, like inside the mirror, if you will, and these are positive lengths. No matter if it's a convex or a concave mirror. I would wager that the most common mistake you guys are going to make today is going to be for the concave mirror, or convex mirrors, excuse me, forgetting to make the focal length negative. Because whenever something changes, you guys make mistakes. So I would guess that that's going to be the biggest challenge for you. But again, you just plug in the same two equations, you just plug in. It's really pretty simple. Alright, that all brings us to lenses. And luckily, lenses just use the same equation. You use the mirror equation for both magnitude and focal length and all that good stuff for lenses also. So I'm not going to talk about these in great detail. But really we have two types of lenses. We have this type, which is called a convex lens. And we've got this type, which is called a concave lens. Okay, these have two focal points, one on each side. Because if we put the object here, it will, for instance, it would converge over here. It would be visible over here, or some such. Not quite exactly like that. But like I said, our same formulas work. 1 over F equals 1 over DI plus 1 over DO, and M equals HI over HO equals negative DI over DO. Okay, so lens problems are going to work basically the same way. You're just going to be asked to find the distance to an object or the distance to an image, or you'll be given those and ask for the focal length or find the magnification or whatever. These are simple formulas. All of these are lengths: focal length, distance, and height. All of those are lengths. Magnification is just a scalar because it's meters over meters. It's just a number. I don't think this is going to be real hard.